Yeah. Okay, thank you. So today we're going to, well, first finish off a little bit of a theoretical discussion about symmetries of QCD. So we will mostly discuss chiral symmetry and see what happens to chiral symmetry in lattice QCD in different formulations. Okay? And then we will finish maybe with a few slides just to tell you a few words about applications of lattice field theory beyond QCD. Okay? So let's start from symmetries of QCD. And start by reminding you a few basic ideas about the way symmetries are implemented in field theories, and then we will specialize to Wilson fermions and Ginsberg Wilson fermions and see how these general ideas apply to these specific examples. Okay, so first of all, we will be interested in global symmetries. Okay, so transformations of the fields, which in infinitesimal form we can write in this version, where phi is a generic field that appears in the action. Now, a symmetry transformation is a symmetry that leaves the action invariant. Okay, remember we said when you specify the action, you basically specify the symmetries of the theory. Okay, so a symmetry of the theory is a symmetry that leaves the action invariant. And in a classical theory, the consequence of symmetry is conservation of the Noether currents. So, in quantum field theory, the equivalent of the conservation of the Noether current are the word identities. Okay? So, the simplest way to derive the word identity is to actually promote this parameter to a local quantity, so a quantity that depends on space-time, and then look at the variation of the action. Now, in general, the variation of the action will be written in this form. Let me tell you what this is. Okay, so this is the usual Noether current. Okay, so you see if alpha is a constant, you integrate by parts, and you get that the action is invariant. And capital delta here, I've added any sort of explicit, I've written any explicit symmetry breaking that you may have in the action, and I've called it capital delta. Okay? So and then it's just a few lines of algebra. You can show that if you take the correlator of the derivative of the Noether current with any sort of kind of probe, where the probe is a generic function of the fields in your theory. I'm just going to write it like that. Okay. This correlation function is equal to correlation function of the explicit symmetry breaking with P. Sorry, P is not a function of X. P is a generic P, plus the variation of P itself under the symmetry transformation, which we can write like that. Okay. Now, if P is just a monomial in the fields, these are the usual contact terms, right? The delta x minus xi, blah, blah, blah. Okay? Does that look sort of familiar? So the insertion of d mu, j mu, in any sort of correlator is equal to, let's say, 0, okay, plus the insertion of the explicit breaking plus contact terms. Yeah? So that's the generic way that symmetries are encoded in a quantum field theory. Okay, so symmetries give you relations between correlators. That's the way they're they are encoded in a quantum field theory. So now let's apply these ideas to our different fermionic formulations. So let me start by writing explicitly the action for Wilson fermions. So remember, in the case of Wilson fermions, we solved the doubling problem by adding an irrelevant operator, so a dimension 5 operator. So when you put all the ingredients together, the action looks like this. So we have a sum over all the sides, and then factor of 1 over 2a. And then we have contribution from the covariant derivative and the Laplacian, which you can write like this. This is the gauge link, which comes from the covariant derivative, plus a similar contribution that comes from the backward derivative, which you can write like that. Everything that is proportional to R comes from the Laplacian that is in the Wilson term, okay? And then plus psi bar x m, which is the bare mass, times 4 R over A times square x, like that. Okay? So everything that is proportional to R comes from the Laplacian, from the discretized Laplacian, and then you have the covariant derivatives from the kinetic term and the bare mass. Okay? So you see here, if both m and r are set to 0, then the action is symmetric under chiral transformations. Okay, let me write explicitly the chiral transformations. Let's take non-singlet transformations in flavor space. Okay, so these are generators in flavor space. Psi x. And likewise for psi bar. Like this. Okay. And then there is another current associated to this transformation, which again you can compute. So I'm going to call this J5 mu A. There is an index A, okay, because these are flavor non-singlet transformations. And so this is going to be 1/2 of psi bar x plus lambda A 2 and 5. So this is a sort of discretized version of the usual axial current. Okay, x mu x plus emission. Okay, and then if we want to compute if you want to write the word identity which is associated to a chiral transformation for Wilson fermions, we're going to have a contribution like that, which involves the nether current. And then we're going to have an explicit breaking. So everything that is proportional to m and r in the action is going to give you an explicit breaking, so a term which looks like delta x. Okay? And then there will be the variation of the probe. Now, this delta x, I'm going to split it into two contributions. One contribution is the contribution that you would have in the continuum theory, so the explicit symmetry breaking that comes from the mass. And then a second contribution, which is the contribution that comes from the Wilson term. Okay? Remember we said a couple of days ago that the Wilson term breaks chiral symmetry, as you can see in this expression, right? And so in writing the explicit breaking in the word identity, I'm going to split these two different contributions. Okay? So I'm going to have a term which is a backward derivative of J mu A5 of x times whatever probe you want to choose. And then on the right-hand side, there will be a contribution from the mass term, which we can write in this form, lambda A over 2m psi of x, like that. Okay. And plus a contribution that comes from the higher dimensional operators. There is a p plus the variation of the probe itself. Like this. Okay? So remember here we have flavor. Okay? So in principle M is a matrix in flavor space, NF by NF, where NF is the number of flavors. So this is the explicit symmetry breaking due to the mass. You have the commutator of the generators of the transformation with this mass matrix. And then this is the breaking which is due to higher dimensional operators, which we introduced in order to remove the doubling. Okay? So, naively, this is a higher dimensional operator, okay? And therefore comes with powers of A. Okay, so it's suppressed by 1 over the cutoff in the theory. However, when you take a correlator, because of quantum corrections, you may have divergences. Okay? So divergences in x of x px imply that the matrix element itself is not of order A. Let me write it like this. Okay? There is nothing to worry about. We've seen this before in quantum field theory. We know how to deal with that. Okay? So we simply need to renormalize the composite operator. Okay? These are just bare fields at this stage. This could be a renormalized operator. These are bare fields. There are divergences. We just have to renormalize the composite operator. So how does the renormalization work? Well, you can define a renormalized operator like this as the original one up to like this. And then you want to subtract the mixing with all dimensions, with all operators that have dimensions less or equal to x. Okay? So in this case, there are only 2, and they clearly correspond to the other 2 operators that appear in the word identities. So the renormalized operator can be written like that. Psi 2 m bar. This is my renormalization constant, psi of x. And then ZA minus 1. This is the other renormalization constant, delta mu star j mu phi a x. Okay? Does it make sense? Yes.
Why do you suddenly have phi?
It's just a generic notation to denote the variation of p with respect to the fields. Okay, so just to make contact to this. So phi here is just a placeholder for any field in the theory. So in this case, you would have to sum. You would need to have the variation of p with respect to psi multiplied by delta psi plus the variation of p with respect to psi bar multiplied by delta psi bar. It's just a shorthand. Okay. Is everybody happy with this? So m bar is a function of g. Okay, and it goes like 1 over a for dimensional reasons. So this subtracts potential linear divergences. This takes care of log divergences. Okay. Now, why did I use this notation? I use this notation because now I can replace x with its renormalized counterpart, and then I can reabsorb the renormalization into the terms that are already present in the word identity. Okay? So if you take this expression, you plug it in, this ZA minus 1 combines with that, okay? And you get a ZA delta mu star mu phi a of x p on the left-hand side. The subtraction of psi bar psi combines with the explicit breaking. And so we get psi bar of x 1 over 2 m minus m bar 5x p. And then here we are left with the renormalized operator. Plus, let me call it delta x p. Okay, so that I don't need to write explicitly the phi's. So this equation here really summarizes what happens, what is the cost of the explicit breaking of chiral symmetry by higher dimensional, so irrelevant operators. Okay? So if you compare the word identity with the word identity that you would get in the continuum theory, ZA is equal to 1. Okay, the axial current doesn't renormalize, so we have a multiplicative renormalization of the axial current, and we have a fine-tuning of the mass, which is necessary. Okay? So in the continuum theory, because of chiral symmetry, you know that m equals 0 gives you the chiral theory. So this is in the continuum. Here, because we broke chiral symmetry with Wilson fermion, we can only recover the chiral limit by fine-tuning. Okay? So there is a parameter to tune in order to reach the continuum limit. In other words, we have an additive renormalization of the bare mass, which in the continuum theory you don't have because of chiral symmetry. Okay? So with Wilson fermions, you break chiral symmetry, you break it by an irrelevant operator, so the long-distance physics is expected to be the same, and what is different is that you need to fine-tune the bare mass. So for every value of the bare coupling, you have to fine-tune the value of the bare mass in such a way that you reach the chiral limit. Now, let's move on to Ginsberg-Wilson fermions and see what we can say about symmetries. In the case of Ginsberg-Wilson, so remember, and here we will focus mostly on the axial symmetry, on the U1 axial symmetry, so on the flavor singlet sector. So remember we said that the Ginsberg-Wilson Dirac operator, I'm going to get rid of the GW, okay, so the D here is always the Ginsberg-Wilson operator, satisfies this anti-commutation relation with gamma 5, okay, so this was our sort of minimal breaking of chiral symmetry in agreement with Nielsen Ninomiya. Okay. You can check that the Ginsberg-Wilson operator is gamma 5 Hermitian, so it satisfies that relation over there, and you can rewrite the Ginsberg-Wilson relation in a couple of ways that are useful. So you can multiply by d minus 1 to the left and to the right, and then you get the following equation, which is a different way of rewriting the Ginsberg-Wilson condition. And you can multiply this by gamma 5, and then you find A gamma 5D, gamma 5D, which is just d dagger d. Okay? Or H squared, where H is the Hermitian Dirac operator, so it's gamma 5D. So these are trivial relations which are going to be useful in what we are going to say next. Okay? So first of all, we can define V. We can define an operator V, which is simply d minus 1. Okay? And then you can show, as an exercise, that V is unitary. Okay? This is the consequence of the Ginsberg-Wilson relation. Now, using the fact that V is unitary, you can immediately derive a result about the spectrum of the Ginsberg-Wilson operator. Okay? V is a unitary operator, so all the eigenvalues of V lie on the unit circle. Okay? So the eigenvalues of D lie on a circle which is centered at 1 of radius 1. Okay, so 0, 1, 2. Okay, so all the eigenvalues lie on a circle. And remember, just for comparison, in the continuum, do you remember what happens to the eigenvalues of D? In Euclidean space, they're all imaginary. Okay, they come in pairs, they come in complex conjugate pairs, and they're all imaginary. So in the continuum theory, the eigenvalues of the Dirac operator are all on the imaginary axis. So you can see here as you are at a small distance from the imaginary axis, this is tangent with a vertical sort of derivative. So for small values, for small eigenvalues in units of the lattice spacing, you are close to a sort of continuum spectrum, and then there is this deformation of the spectrum, which is due to the discretization. Okay. So, why is this useful? This is useful because, first of all, it allows you to write an index theorem in a very simple way. So, if you consider quantity I'm going to call nu, which is a over 2, and the trace of gamma 5 d. Okay. Where the trace here is over all sort of indices, so position, color, spin. Okay. Now, you can rewrite this as minus a trace of gamma 5 times 2 minus a d. Okay. And by inserting a complete set of eigenstates, we can rewrite the trace in the following form. Here we are summing over all the possible eigenvalues. Then we've got v lambda dagger, gamma 5 minus 18 v lambda. Okay? Where v lambda are eigenvalues of d with eigenvalue lambda. Okay. And so we can rewrite this expression here as minus 1 over 2 times the sum over lambda times 2 minus a lambda, and then v lambda dagger gamma 5 lambda. Now, there is you can show, this is one of the exercises. I have to remember to leave the problem sheets behind. I forgot to give them to the organizers, but one of the problems in the problem sheets is precisely to show that this scalar product, okay, so v lambda dagger gamma 5 v lambda is equal to 0 unless lambda is real. Okay. So, in computing this trace, okay, where you sum over all the possible eigenvalues of d, because of the gamma 5 structure, so because of this coefficient, you see that you get contributions only from the real eigenvalues of the Dirac operator. So there are only two places that contribute. This is lambda equals 0 and lambda equal 2. Now, because of this factor, sorry, this is lambda in units of A, obviously. So because of this factor, the contribution from A lambda equal to 2 is actually 0. Okay? And so you only get a contribution from the 0 modes of the Dirac operator. So this is just a way of counting the 0 modes. And now for the 0 modes, this factor here gives you a factor of 1 if you have a mode with chirality 1, and minus 1 if you have a mode with chirality minus 1. Okay, so this is simply the number of left-handed 0 modes minus the number of right-handed 0 modes. These are the left-handed 0 modes of D, and R are the right-handed 0 modes of D. Okay. So, this is this is your index theorem. Okay, so you've got a quantity nu, which is given by taking the integral over the entire space of the trace in color and spin indices of gamma 5 dxx. Okay, so this is some complicated function of the gauge fields. Remember that the gauge fields enter in the definition of D. Okay. We are not going to write explicitly the dependence on the gauge fields. There is nothing to learn from it. Okay. But this specific combination, counts the number of zero modes. Okay. So this is exactly the equivalent of the index theorem that you have in the continuum. So nu is a discretization of the topological charge of the theory of a given configuration. Okay. So in the continuum limit, this is just the integral over dx of g tilde. Okay, so this gives you a way to define the topological charge density Gg tilde on the lattice. So having done this, we can now go back to the axial word identities and discuss the axial anomaly. So we're not going to do the entire derivation. We already mentioned that in a previous lecture. We're just going to focus on what is specific to the singlet sector. So if you remember, in discussing symmetry transformation, at some stage I mentioned the fact that the measure in the path integral was invariant under chiral rotations. Okay? At that time we were talking about non-singlet chiral rotations, and we said that the measure in the path integral was invariant. Now, we're going to look at the path integral measure for the specific case of chiral symmetry for Ginsberg-Wilson fermions, and we're going to see what happens to the path integral measure. Okay, so we're going to take the sort of lattice version of chiral symmetry that we introduced a couple of days ago. So remember, this is an exact symmetry of the theory at finite lattice spacing, finite cutoff. So psi goes into, if you remember, this is just a generalization of the usual chiral transformations. So gamma 5 times 1 minus, let's say, a over 2d, like that, minus psi, and psi dagger goes into psi dagger 1 plus I epsilon m times 1 minus a over 2d times gamma 5, like that. Okay, where M is a matrix in flavor space. So when M is lambda A over 2, we get non-singlet axial transformations. And if M is equal to the identity, we have singlet axial transformations. So remember, this is an exact symmetry of the theory. This leaves the Ginsberg-Wilson action invariant, which you can show by simply using the Ginsberg-Wilson relation. Okay. And now what we really want to do is to check what happens to the path integral measure when we do this transformation. So this transformation induces a Jacobian in the path integral measure. So we can write d psi, the measure d psi prime, sorry, d psi prime, d psi prime bar as d psi bar, and then get the determinant of the Jacobian. So we get the determinant of 1 plus I epsilon m gamma 5 1 minus a of 2d, like that, and then we get another determinant from the transformation of psi bar. Now for an infinitesimal transformation, remember that the log of the det is the trace of the log, okay? So you can replace the determinant with the exponential of the trace of the log, and then you can expand everything linearly to first order in epsilon, okay? And so, does it make sense? I mean, did I say something that you're familiar with? Yeah? Okay, good. So, exponential trace log, this is log of 1 plus epsilon, so you expand the log and then you expand the exponential, and so the final result is 1 plus 2I epsilon. There is a factor coming from this determinant and a factor coming from this determinant here, so altogether you get a factor of 2, and then you get a trace, and this trace is overall indices of M. This is our matrix in flavor space, and then we get gamma 5, 1 minus a over 2d, like that, and that's it, at first order in epsilon. Okay, so in particular, in here, you need to take the trace over flavor. The only thing that depends on flavor is M, okay? So let's write just another line to make it fully explicit. We get 1 plus 2I epsilon. Then we have a trace which is only over flavor of M, and then we have a trace of the rest. Okay. So here you see immediately two things. First of all, if you are dealing with a non-singlet transformation, then this matrix M is a generator of SUN, okay? And so it's traceless. So this Jacobian factor vanishes. This is the example that we discussed already, that I mentioned already in the lectures. If you have a non-singlet transformation, then indeed the integration measure is invariant. Okay? If you have a singlet transformation, then this is the trace of the identity. Okay? So it gives you a contribution which is just the number of flavors. So you get 2I epsilon times the number of flavors times the trace of gamma 5, 1 minus a over 2d. Okay? And this is exactly the anomaly. Okay? This is the U1 anomaly, and here you recognize so the trace of gamma 5 is going to be 0, and then you're going to have a term which is the trace of gamma 5 a over 2 times d, which is exactly my topological charge. Okay? So you get an anomalous contribution. I'm just going to write it in words. Okay? So we get an anomaly which is proportional to the trace of a over 2 gamma 5 d, which is exactly the topological density. Okay? So this is the derivation of the axial anomaly. It's the, I think it's the cheapest derivation you can get of the chiral anomaly. Okay, and it's all encoded in the properties of the Ginsberg-Wilson operator. Okay, so the properties of the Ginsberg-Wilson operator determine the spectrum of the operator. Because of the spectrum, you find out that this trace of gamma 5D is really an index of your configuration, and that index is exactly the term that appears in the determinant when you do a flavor singlet axial transformation. Okay, none of this is by accident. Okay, any questions? No. Okay, good. So now we are going to finish off by quickly discussing how to do a lattice QCD simulation. You know, what is actually computed. How do you extract any information out of the quantities that are computed, and then maybe I'll say something about applications that are beyond QCD. Okay. So let's consider a series of operators. Okay, we're going to have a sort of a pseudoscalar density, which we're going to define like this. So these are my quark fields again. These are the flavor index. Okay, here we plug a lambda A or lambda A over 2 psi of x. Okay, so this is called pseudoscalar density. We're going to consider an axial current, just to give you a few examples. Okay. X, gamma 5, gamma mu, lambda A over 2 psi of x. We're going to consider vector currents. And having defined this interpolating, these are called interpolating fields, sometimes for reasons that are going to be clear in a second. What you actually compute are typically correlators of these objects. Okay, so for instance, you can take pseudoscalar correlators at a Euclidean distance x4. This is defined as the sum over all the spatial positions of PA of x4 x PA of 0. Okay. So what you compute by numerical simulations is this expectation value here. Okay. So when you do a lattice simulation, everything that is an expectation value is computed by Monte Carlo methods. Again, I'm not going to talk about Monte Carlo methods in this course, but basically you have a numerical way of computing these correlators. And so, provided you have enough computing power, you can compute correlators up to a given statistical accuracy. Okay? So all the correlators are computed by Monte Carlo methods. So typically, you're able to compute 2-point functions, 3-point functions, or more complicated correlators. Okay? And then the game is to actually extract some physical information from the behavior of these correlators. Okay? Now, if you go back to the very first lecture when we discussed the transfer matrix, for instance, okay, you will see that there is an expression for a 2-point correlator in terms of the trace of powers of the transfer matrix, insertion of the operator, powers of the transfer matrix, insertion of the operator. Okay? So if you use that kind of formula, you can actually show that this correlator here is given by a sum over all the states, okay, I and j are the possible states, of some spectral coefficient, Cij, times a function h of x4, which depends on the energy of the two states Ei and Ej. Okay? So in a finite box of extent t in the fourth direction, you can show that this correlator, so the x4 dependence of this correlator can be written like that. So there is a contribution from every state in the theory. Now in the case of QCD, these are your physical states, okay? So these are the hadrons. They are the states of the physical spectrum. So this sum here of I and j goes over all the hadrons, even though not all of them will contribute for symmetry reasons. And this function h is given by the following expression, and as an exercise, you can derive the expression for h. So h of t e prime is the exponential of minus e t minus e prime, capital T minus t, where capital T is the total extent in the fourth direction of your lattice, plus the exponential with e and e prime exchanged. So e prime t minus e t minus t, like that. Okay? Now, where the energy eigenvalues here are ordered, okay, so E0 is your ground state, which is set equal to 0. The E1 is the lowest energy state, and so on. Okay. And if you take the limit of this expression for capital T that goes to infinity and x4 large, okay, so FPP of x4 when t goes to infinity and x4 is ax4 is much x4 over a is much larger than 1, you see that this sum is dominated by the lowest energy state, and so you get a single exponential decay. Like that. Okay. Where GPS is the matrix element of the pseudoscalar density at 0 with a pseudoscalar state. Okay? And so, first of all, you see that, in general, all these spectral coefficients here are given by expression of this kind, okay, where you have the matrix element of the interpolating operator with some physical state, which is why they are called interpolating operators. So the only states that are going to contribute to that sum are states such that the quantum numbers allow this matrix element to be different from 0. Okay? So the quantum numbers of your interpolating field dictate which states are going to enter in that sum. Okay? And amongst all the states, when you go to large distances, the lightest state is going to dominate and is going to give you a single exponential decay. So you compute correlators correlators. You look at the long distance behavior, so large values of x4, and you find that these are single exponentials with coefficients. So the rate of the exponential decay gives you the spectrum of the theory, and the coefficients in front give you the matrix elements of the interpolating fields with the physical states. And remember, these are the physical states, okay? These are the eigenstates of the Hamiltonian. So the states that appear here are the physical states. So you get all the strongly interacting dynamics already built in. Okay? So with that, you can start computing the spectrum. Now again, let's assume that you're working with two flavors, two degenerate flavors. So in the theory, this is what we briefly mentioned yesterday. So if you consider an SU3 lattice gauge theory with two degenerate flavors, then there are only two relevant parameters, so G or beta, if you like, as we said yesterday, and M, where M is the mass of the two degenerate flavors. Okay. And so you need to tune. This is something we already discussed yesterday, but I may just as well repeat it today. You can tune, you have to tune, okay, G and M in order to get the correct physics in the infrared. And the way that this is usually done is by working in mass-independent schemes. Okay? So you fix, let's repeat that, in a mass-independent scheme, you fix G, but you choose a value of G. Then, using this kind of correlators, you can compute masses. Okay, let's say you compute the mass of the vector state and the mass of the pseudoscalar state. Okay. So, for a value of M, you compute on the lattice AM vector over AM pseudoscalar. Okay, and you tune M so that this is equal to the experimental value of MV over MPS. That gives you M as a function of G. And now if you want to find G as a function of A or A as a function of G, okay, you look at one of these, you look at any dimensionful quantity. Again, on the lattice, you will measure E M omega, where omega is a generic state, okay, and you require that this is equal to the experimental value of M times A, and so the lattice spacing as a function of G is the experimental is AM omega. This is the quantity that you compute on the lattice divided by the experimental value. Okay. By the way, I should have said it here. Okay. What you get from these correlators is always the spectrum in units of 1 over A, right? Because this number here is actually A MPS times X4 over A. Okay. So this is the discrete So this is the integer that characterizes the position of your point on the lattice. Remember, on the lattice you don't have A, right? When you write a computer code, there are no GeVs, there are no Fermions. Okay? In the actual computer code, everything is written in units of A. Okay? So what you measure is really, so what you see is really a decay which goes like that. Okay? Where n4 is the integer that characterizes your position in time. So what you extract from a lattice simulation is always masses in units of A, right? Which is why here I always write masses in units of A. So this is what you compute in the numerical simulation. This is what you compute in the numerical simulation. You take the ratio and you set it equal to the corresponding ratio in nature. Okay? And likewise, in order to determine the scale, you compute this dimensionless quantity. This is the result of a lattice simulation. This is something that you measure, and the ratio of these two tells you your coupling. Okay? Sorry, your lattice spacing as a function of the coupling. And then you can invert these relations, okay? And you get G as a function of A and M as a function of A. And this is exactly your RG trajectory of constant physics. Okay? The physics is determined by the ratio of two masses and the experimental value of one of them. In this case, right? Here we only have two relevant parameters, so we need two experimental inputs to completely specify the theory. In this case, we can take the ratio of two masses and one of them. Once I specify these, I can build my RG transformation, and so I can do a series of simulations at different values of A, and I can get towards the asymptotic regime where A is sufficiently small compared to the scales that I'm interested in, and I get continuum physics up to power corrections. Does that make sense? Yeah? Okay. Good. So this is what I'm going to write about, and then I'll spend the remaining sort of time, or maybe a fraction of it, showing you a few examples of applications of lattice field theory beyond just QCD. Okay, so these are RG flows as we discussed. Okay, so we have fixed point at the origin. This is the Gaussian fixed point. This is the ultraviolet fixed point for an asymptotically free theory. Okay, and then as you move away from the fixed point towards the infrared, there are these red curves which are renormalization group trajectories. Okay, this RT here means that it's a renormalization group trajectory. So it's a trajectory of constant physics. Okay, so you can have several examples. So if you consider just a pure Young-Mills theory, then there is an ultraviolet fixed point. There is only one relevant coupling, which is the gauge coupling. Then there are infinitely many irrelevant couplings, and so you only need one sort of renormalization condition to sort of determine your renormalized trajectory. Okay, and so in general, if you start a simulation in a point somewhere in parameter space, provided you tune your relevant parameter, eventually you will flow to the sort of renormalized trajectory in the infrared. So you will get the correct physics at low energies. QCD is a theory like that. Okay? So again, you have the asymptotically free Gaussian fixed point in the ultraviolet, but now there are two relevant directions. Okay? And so the space of renormalized trajectories is a two-dimensional manifold. Okay? So there's an entire plane of trajectories that come out of the fixed point. And they basically correspond to trajectories where the quark mass is different. Okay? If you change this value, you move along different red trajectories. Okay? Does that make sense? So one of them is the actual QCD. Is the trajectory where these ratios have the value that we observe in nature, but then there are many other theories where the mass of the quark is different and therefore the spectrum is different, and they are described by this two-dimensional manifold of theories. Now, for some time, there's been some interest in the possibility of having an infrared fixed point. So, the idea that the flow that comes out of the ultraviolet fixed point actually ends somewhere else. Okay, so that, see, along this line, you have a theory which is running. The coupling is running, but in the infrared, the coupling actually ends up in a fixed point. So these are theories that in the infrared behave like a conformal theory. Okay, so these are theories that are scale invariant at large distances. And for a while there has been some interest in theories of this kind for model building, for trying to build models of strongly interacting dynamics beyond the standard model. Whether this is successful or not, we may know in the future. But I think from the theoretical point of view, it is still interesting to ask whether you can see any evidence of an infrared fixed point. Okay, so suppose there is a theory like that. Okay, the theory that at high energies looks very much like QCD. You've got asymptotic freedom. You've got the usual logarithmic running. And then as you go to low energies, you see that the running eventually stops and you get a fixed point. How can you identify such a theory? Okay? So the prime example of this kind of theories are Banks-Zaks theories. Okay? I don't know if you've ever seen Banks-Zaks theory. If you take, do I have a slide about that? No. So if you take QCD, okay, if you take QCD, and you look at the coefficients of the beta function, so beta of B is minus B0 G cubed minus B1 G5 plus higher orders. Now, if you have NF flavors and let's say SU3, you know that B0 changes sign. Okay, so B0 is positive for NF less than, where does it change sign? 33 over 2, I think. Is that 33 over 2? I think it is. At 17, okay? Until 17 flavors, B0 is positive and the theory is asymptotically free. Okay, this is because B, I think, if I remember correctly, B0 is proportional to 33 over 2 minus NF or something like that. Okay? Now, if you go above, then you lose asymptotic freedom. However, if you look at B1 is also positive for in perturbation theory, right? For NF smaller than some NF critical, which I cannot remember, but which is smaller than 17. Okay? So there is a window in the number of flavors where if B0 and B1 are both positive, the beta function looks like that, but there is a window where B0 is still positive, but B1 becomes negative, and then the beta function looks like this. Okay. Now this is the usual ultraviolet asymptotically free theory, and this is a theory that is asymptotically free in the ultraviolet, but then runs, slows down, and eventually is conformal at large distances. Okay, so these theories are called Bang-Sachs theories. It's a perturbative result. Okay, it's a result which is entirely based on the expression of the coefficients of the beta function in perturbation theory. So if your fixed point is at small values of g, you may trust these results, but then the dynamics is not particularly interesting because the theory remains perturbative all the way until you get to the fixed point. But you can also imagine a more general scenario like this, where this fixed point is at strong coupling, and then there could be some interesting strong dynamics over here, and the question is, can we actually identify these fixed points by numerical simulations? So the way to look for fixed point, at least one of the ways that we considered, was to exploit the Kalan-Szymanczyk equation that I wrote down in the second lecture, okay, and try to derive scaling relations for the mass spectrum. So let me talk through how this works. So this is exactly one of the correlators that we were discussing here. Okay, so this H is a generic interpolating field for an hadronic state. So H can be any of these bilinears. Okay, and then depending on what spin structure you choose, you can spin and flavor structure you choose here in the middle, you can select the quantum numbers that you're interested in. Okay, so you can choose the transformation properties of this bilinear so that you select the states that are going to enter in the spectral decomposition. Okay, and then, as we just said, at large Euclidean time, you expect these correlators to decay exponentially, and the decay rate gives you the mass of the states. Now we can do an RG transformation. This is exactly, if you remember, the RG transformation that I wrote in the second lecture. Now, in the second lecture, I had a generic product of fields. This instead is specialized to the case of these 2-point functions. Okay, so I'm changing the scale here by a factor b. Okay, and I am retuning the Baire parameters in such a way that the physics is invariant up to the normalization of your fields. Okay, so if you can remember back to Tuesday, that's exactly the RG equation that we had at the beginning of the lecture. And then if you are remember, again, we discussed this on Tuesday, if you are in the vicinity of a fixed point, the scaling of these coefficients, the running of these coefficients, if you like, is given by a power law, which is characterized by the eigenvalues of the linearized evolution of the linearized RG flow. Okay? So this is stuff that we already introduced on Tuesday. Okay, so it tells you how the correlator depends on the Baire parameters and the cutoff, which here I'm calling mu. Okay. Now you can combine this with naive sort of dimensional analysis. Okay, naive dimensional analysis means that you simply rescale all the dimensionful quantities by a factor of b. I mean, here, remember, I'm using the convention where all the couplings are dimensionless. Okay, so here in the mass, I've already extracted the powers of the dimensions in units of mu in this case. So this is a dimensionless quantity. So when you do dimensional analysis, you get this kind of relation where dH is the naive dimension of your interpolating operator, right? So this is just a change in the units that you use to measure distances, if you like, okay? You've got centimeters on one side and inches on the other side. So if you combine the RG transformation and sort of naive dimensional analysis, and in this expression here, you choose B in such a way that M prime is equal to 1. So B becomes a function of M, and you plug it in here. You see that these 2-point functions, when you're close to an infrared fixed point, do not depend independently on T and M, but they depend on this. They depend on this. Can do that. Yeah, but they depend on this product T times M to a given power, which is given by the critical exponent, okay, by the eigenvalues of the linearized evolution. So remember, all the linearized evolution is valid only in a neighborhood of the fixed point, so it's valid only at large distances. Okay, the fixed point here is the infrared fixed point. So you expect this kind of scaling at large distances. Okay, when you're close to the fixed point. So when you're close to the fixed point, the 2-point correlator is not a function of T and M, but it's a function of this combined so-called scaling variable. Okay. Now, if you compare this expression with the single exponential decay that you expect from the spectral decomposition, you see that MH, so the masses of the particles in the spectrum, have to scale like M to some power. And that power is fixed by the eigenvalues that characterize the fixed point. Okay? So if you have an infrared fixed point, the states, the masses in the spectrum scale, all of them, all states in the spectrum, scale in a way that is entirely dictated by the eigenvalues of the RG flow at the fixed point. Okay? So this is very different from, so you see, this kind of analysis tells you that this kind of theory, where all the states go to 0 as you send the quark mass to 0, is very different from QCD, right? I mean, in the QCD spectrum, as you send the mass to 0, all your hadronic states will converge to some value, which is what you find in the PDG, except one, except the pions, except the Goldstone bosons. Okay, so the spectrum of QCD basically is dictated by chiral symmetry. Okay, so the Goldstone bosons of chiral symmetry become massless as you send the quark mass to 0, while all the hadronic states in the spectrum remain massive. Okay, so this is the proton, the rho, right? They all live up here, and they're not sensitive to the fact that you send the quark mass to 0. The only state that becomes light is the pion. So at large distances, at very low energies, QCD is just a theory of pions, okay? And because pions interact with the interaction that is proportional to the momentum, as you go to very low energies, QCD is just a theory of free pions. Okay? These conformal theories, I mean, infrared conformal theories, the entire spectrum goes to 0, collapses to 0. All the states become massless as you send the mass of the quarks to 0, which, if you think, is sort of intuitive in the sense that the fermion mass breaks conformal invariance. So as long as you have as long as you have an explicit breaking of conformal invariance, you can have massive states. As soon as you switch off the breaking, the explicit breaking, if the theory has an infrared conformal fixed point, you expect all the states to become massless. Because, a massive state would break scale invariance. A massive state is not scale invariant. Okay? And so, while in a QCD-like theory, you have a spectrum that is dictated by axial symmetry, in an infrared conformal theory, you have a spectrum which is dictated by conformal invariance, by scale invariance. Okay? So in principle, studying the spectrum of the theory, you should be able to distinguish the two cases. Okay? Now, of course, I'll show you some results. I mean, these are results that we obtained quite a while ago, I mean, a few years ago. So this is the result of lattice simulations of a theory which is supposed to have an infrared fixed point, which is conjectured to have an infrared fixed point. This is an SU2 gauge theory with two fermions in the adjoint representation. Yes? Sorry.
Yes. Your lambda hadron in the last slide.
Yeah.
On the left. Does that depend which angle you're approaching this fixed point at?
Yeah, of course. The absolute, so,
You can have any one.
Yeah, these theories will have a different spectrum, okay? But it will always be finite. That's the important thing, right? That the hadronic spectrum will be at some value, which depends on which theory you choose, absolutely. What is important is that it's finite. So all these lines have a different typical hadronic scale, right? We live on the line where the typical hadronic scale is 1 GeV. That's where the proton sits, more or less.
It's the same lambda that we saw.
Yes and no. Remember, yes, in the sense that it's a scale, and so you can always write one scale in units of the other. And yes, again, because this lambda that we saw the other day comes out of the fact that the theory is running, and the running of the theory is what breaks scale invariance, right? The beta function, a non-vanishing beta function is what gives you the scale anomaly, right? So yes, as soon as you have running, you can define a lambda parameter in a given scheme. Okay, so yes, the fact that there is a finite scale that emerges is exactly the same phenomenon that we discussed the other day. Of course, the value is scheme dependent. Okay, so when I say we live in a theory where the typical hadronic scale is 1 GeV, I'm just thinking about the proton mass. I'm not thinking about the lambda parameter. The lambda parameter is a number which, depending on the scheme, can take very different values. But it's important that it's non-zero. Okay? While in this kind of scenario, you don't have a typical hadronic scale. You can still define a lambda parameter in this kind of scenarios because the lambda parameter, remember, is really an ultraviolet quantity, right? So it comes from the running down here. But the spectrum, which is an infrared property, will have to go to zero as you switch off the mass. Okay? So let's have a look. I was saying this is data, right? So this is SU2 with fermions in the adjoint representation, which is the reason why I kept this suffix R when I was discussing gauge invariance, right? You can think of lattice field theory that have matter, that have quarks in a representation that is not the fundamental representation, and this is exactly this ratio here. Okay, computed exactly like this. So we took a pseudoscalar interpolating operator, a vector interpolating operator. We computed two-point function. We extracted the mass of the pseudoscalar state in units of the lattice spacing. We extracted the mass of the vector state in units of the lattice spacing, and then we took the ratio. Okay, and this is the ratio as a function of the quark mass again, here in units of the lattice spacing. Okay? So the chiral limit is down here. You don't want to go too far away in this direction. Why? Because of lattice artifacts, right? This is the continuum limit. I mean, where you describe continuum physics is down here. You don't want to go there. However, your simulation is much cheaper here than it is there. Okay, that's why we started so far away in the sort of with relatively heavy quarks, and then we started getting lighter and lighter. As you get lighter and lighter, you see that the error bars increase. This is simply because the simulations become increasingly expensive. For those of you who have ever done numerical simulations, and so this was the final result at that time. Different colors correspond to different lattice sizes, just to check for finite volume effects. I mean, let's not get into the details, but this is what we found. Okay, so if you look at that on this scale, it looks rather messy. If you look at the axis, it's not so bad actually. Okay, so it's just a few. These are fluctuations by just a few %. And what you see here is that this ratio seems to go to a constant. Okay, let me say goes to a constant as you send the quark mass to 0. This is exactly what you expect for a conformal spectrum. Okay, so all the states in the spectrum go to 0. They all go to 0 with the same critical as a function of the mass with the same critical exponent. So if you take the ratio of the masses, you expect this to go to a constant, which again is different from what you expect in QCD, right? In QCD, you have, because again the spectrum is dictated by chiral symmetry, as you send, so the mass of the vector, as you send the mass of the fermions to 0, is going to go to a constant. Let's call it MV chiral. And the mass of the pseudoscalar, as AM goes to 0, is going to go to 0. Right? As the square root of the fermion mass. And so if you look at this ratio for a QCD-like theory, this ratio actually blows up. Okay? So with the limited statistics that was obtained at that time, this was sort of in agreement with the idea that the theory could be conformal. Of course, a numerical simulation will never give you a theorem, right? You need to know what you're looking for, and then you can check whether the data agree or not. Now, in order to get a little bit more confidence that what we had many more results for the spectrum, and they're all in agreement with the idea that with the hypothesis that the theory is conformal. Now, in order to get sort of more confidence that we were indeed looking at the infrared fixed point, we looked at the running of the coupling using the Schrödinger functional, so in the same scheme that we discussed yesterday, right? So you put, while here we were trying to go to the largest possible lattices in order to get rid of finite volume effects, here we work in a finite box, so the physical size of the box is finite, okay? And we use the volume of the box as a probe to run our couplings. So just like we discussed yesterday, we can define a coupling in this Schrödinger functional scheme from an observable, okay? So this is the expectation value of the derivative of the action with respect to eta. Remember, eta is this parameter that enters in the boundary condition. The details, again, do not matter, right? I mean, what is important is that this is an observable. So this is something that you can compute, again, as I said, by Monte Carlo methods, okay? So you have a non-perturbative estimate of your coupling at a scale which is given by the size of the box, and this k is just this factor of 12 pi that we had yesterday. Okay. So we did that, and again, this is a brief sort of recap of what we said yesterday. We defined a step scaling function on the lattice, okay, which has got lattice artifacts that go like 1 over the number of sides that you have in your volume, and this step scaling function is measured by measuring this coupling in a volume L over A and in a volume which is bigger by a factor S. Okay, it's exactly what we discussed yesterday. So you see this sigma is entirely defined in terms of quantities that you can measure in a numerical simulation, namely this renormalized coupling and this renormalized coupling. Okay? And then you need to do multiple simulations so that you can actually extrapolate this capital sigma to the continuum limit, so you can get rid of the discretization effects that are unavoidable when you do a lattice simulation with a fixed cutoff. Okay, so you perform multiple measurement of this capital sigma until you can take the limit where A over L goes to 0 in a controlled way, okay, where in a way where the extrapolation is sufficiently well defined by the data. Okay. The devil is in the details, right? In order to do that, you need to run a lot of simulations. Okay, so you want this extrapolation to be a controlled extrapolation, so you need a lot of small values of A over L. Small values of A over L means many, many points in your simulation. Anyway, it's doable, it can be done, it has been done in QCD, and it has been done for these conformal, infrared conformal theories. Okay, so if you have a fixed point, you expect the step scaling function to give you sigma of u equal to u. Okay, so if the theory has got to a fixed point, the coupling is no longer running, so the coupling at different scales is exactly the same, which means that this ratio is simply equal to 1. Okay? Now, so far, so good. You can expand your coupling, you can expand the beta function around the fixed point. You can sort of write down what you expect. You can write down the behavior that you expect for the step scaling function close to an infrared fixed point. What is the tricky part here? The tricky part is that as you approach the fixed point, by definition, the running becomes very, very slow. Okay? So now if you look back at the way the step scaling function is defined, the step scaling function is defined as the value of the coupling on a bigger volume given the value of the coupling on a smaller volume. But as you get close to a fixed point, this number is very, very close to this number. Okay? And so you need an extremely precise simulation in order to be able to pin down the behavior of the step scaling function where it is interesting, so namely close to the fixed point. So with these sort of caveats in mind, I think I can show you what we got. So this is this ratio sigma u over u. So this is 1, remember, at a fixed point. So you have the ultraviolet fixed point here for the renormalized coupling equal to 0. Okay. Then you go out of the fixed point, and this does what it does, right? So for small values of the coupling, you can use the one loop and the two loop expression of the beta function. And yesterday we saw the relation between the step scaling function and the beta function. So you can actually compute this ratio in perturbation theory, and these are the blue and the green line, respectively, at one loop and two loops. So the two-loop result for this theory looks like this, right? So if you look at the two-loop result, there is an infrared fixed point. So this green line eventually sort of goes back down and crosses the y equal 1 axis somewhere at very large values of the coupling. The points here are the results of the numerical simulations. So I'm going to tell you briefly what the different colors mean. I mean, the points, there is only one set of points, and the different colors correspond to the errors in the calculation. So the black error bars is the statistical error. So if you only look at the statistical error, everything looks great. You have an infrared fixed point down here. The red error bar is the error bar that you get in the, because, okay, I've skipped some of the details, but anyway, it's an error that comes with the fitting procedure, and it's asymmetric because of the behavior of the function in the different regimes. Okay, it's not great. It's not great, but fine. You can survive, and with a little bit of ingenuity, maybe these errors are always asymmetric, and with a little bit of work, you can probably get rid of this asymmetry. The real killer there is the gray error band, which was in gray too, because we were all hoping that it wouldn't be visible when we first presented the result. And this is the systematic error that you get because of the slow running. So at some stage, the error, you see here, the error in your so this is related to the continuum extrapolation, and the error that you make. So to be able, you see, here you are trying to take a continuum extrapolation of something that is a tiny change, right? And so what this gigantic error bar here, gigantic again, look at the scale, right? It's a few percent. But the point is that the effect that you're trying to see as you get closer and closer to the fixed point is a very tiny effect compared to the lattice artifacts, okay? And so, it's very nice, it's a very nice idea, but it's extremely expensive to actually be able to perform a continuum extrapolation that is reliable when the effect that you're trying to detect is so small. So this is fairly old. It's a fairly old result. The reason I'm showing you this old result is because we didn't get a better result in time. It's not something that you beat by brute force. I mean, you need better ideas. There are better ideas, but they become very quickly sort of complicated. I mean, we can discuss that offline. So again, you don't get a proof. You never get a proof by a lattice simulation. Again, you look for consistency. This is consistent to some extent. Of course, the systematic error is killing you. So if this were the only result that you had, you would be crazy to claim that you're seeing an infrared fixed point. But when you start combining the fact that the beta function bends down with the fact that the spectrum is indeed sort of conformal, again, it's not a proof, but it starts to give you some confidence that maybe these theories do have an infrared fixed point. Now, I don't have time to introduce all the technology. By looking at other quantities, you can also determine the critical exponents. And one of the reasons we didn't invest more computer time into that is that in order to do some useful phenomenology, you like these critical exponents to be relatively large. I'm looking at Giuliano because he's an expert in this kind of games. And actually, in these kind of theories, the anomalous dimensions are not big enough to make them really interesting for phenomenology. So, it's sort of, it's still there. I mean, I think theoretically it's a very nice problem to be able to identify, something new, sort of a new sort of field theoretical behavior by lattice simulation. The results are encouraging. I think we definitely see a behavior that is not QCD, that is not QCD-like. We are able to compute the critical exponents. Doesn't look great for phenomenology, but then nature has not been very kind to us. So, it doesn't look great for physics beyond the standard model, but then we've not seen much beyond the standard model. So the reason I'm saying that is not because I'm saying it's not interesting, is because if we had seen something, we would have much more guidance, okay, in choosing our theories. Okay? So here, you see, if you want to use this as a theory, as a model for physics beyond the standard model, you have to commit on a given UV completion, right? You are choosing a specific theory. So here I'm saying, beyond the standard model, I have an SU2 theory with fermions in the adjoint representation. What are the chances of this being true? I don't know, 0, right? I mean, but it's still interesting because you develop the technology, you develop the method, you solve, if you like, the theoretical problem. But, imagine that there is really some strongly interacting physics beyond the standard model. We've only seen the Higgs boson. Okay? So the Higgs boson would be a composite state of this new theory. Can you guess QCD having seen only pions? Probably not. Okay? So it's still interesting to do non-abelian gauge theories. So this is where we are. We will see what happens in the future. There is still plenty of time. I think solving the theoretical problem is by itself a useful and a worthwhile sort of exercise. And as for phenomenology, we will see. Well, you will see. There's plenty of time. Okay, and I'll stop here. Thank you.